there?
Yes, I'm there.
Okay, so if you're okay, maybe we can start. So, welcome everyone. It's a great pleasure to have Zahra for be our speaker today from Lisbon, and he's going to talk about exclusion process with next nearest neighbor interaction. Ali, the floor is yours, and thanks for accepting our invitation.
Well, thank you, Zahra. Thank you for this nice invitation. So this work that I'm going to talk about is joined with Gunter Schütz. I did it here recently during my postdoc in Lisbon. So the title exclusion process with nearest neighbor interaction. I will first provide a definition and basic properties, including the invariant measure of the model. Then I will speak about q-Catalan numbers and how they help us to compute the partition function, and as well, how do they help us to extract the asymptotic behavior of the large systems. Okay, so first, the model is very similar to exclusion process. So you have particles who can hop backward or forward with different rates, except that the forward hopping is conditioned on the site on the left be empty. So this particle can jump with rate q if only on the side on the left is empty. So this, for instance, this one cannot jump because on the left it's occupied. And the backward jumping is conditioned that the site k minus 2. So this 2, that you have two sites empty behind you. Okay. So for instance, this one can jump while this one cannot jump because it has only one available site. So to jump on the left, you need two available sites on your left. Okay, so this model, first, if you take q equal 0, so you have only backward jumps, you can map it to a facilitated exclusion process. You simply exchange the whole particles and you exchange the direction of the space. Okay, so this model, the facilitated exclusion, it was introduced originally by Helbing in 1999, and then further studied by Basu, Gabel, and by different occasions. So, okay, my model or our model, it inherits some of the properties of the facilitated exclusion process, in particular for systems which are more than half filled. The system gets blocked because you get many ergodic component, and the evolution of the system is blocked. While okay, for systems which are less than half filled, okay, of course for facilitated it would be the other way around, because we have particle hole exchange. So for systems which are less than half filled, then there can be a current. The system is not blocked. Okay, but it has as well, like our model has intrinsic properties which are different from the facilitated exclusion process, and in particular for systems which are less than half filled, the invariant measure is complicated. It's not as simple as for FTASM, and for exactly half filling, the model is much more richer. Okay, that's what I'm going to show. Okay, other like special cases, which is for b equal to 0. So you have many absorbing states. Actually, any two neighboring particles will just form a block, and they cannot anymore move. Okay, so it's not very interesting. So for the moment, I will just consider that b is not 0, and you can rescale it to 1. So that's what I will do for the next slides. Some particular case as well, which is should simplify the dynamics, which is p equals q. So this is, you just have a uniform measure. Okay. So okay, first to go further, I need to define the height function for a system, for half-filled system. So the half-filled systems are the systems that I'm going to consider in this talk. Okay, so this is like the case that I studied. Okay, and the height function is defined like as usual. If you have an empty space and a void, you just your height function increases by 1. If you have a particle, it decreases by 1. Okay. So yes, like here, for instance, if this particle jumps forward, then the height path will evolve in this way. It can increase this. You can speak about surface dynamic here. So this part of the surface can evolve upward, or this part of the surface can evolve downward if this particle jumps to the left. Okay? So there is some properties of basic properties of the system, okay, with half filling always. Okay. First, the minimum of the height is conserved. So the minimum of the height is just defined as the minimum of this function. So over the lattice. Okay. It's conserved. And how do you show that? Okay. Assume that that the minimum is somewhere, let's say at this point, like this green point, and it's about to evolve. Okay, if it's about to evolve, now if you look at the configuration on the left of this minimum, first it cannot be this red segment, because if it's this red segment, then it will not be a minimum, and there is another minimum. So it's not okay. On the left as well, it cannot be this other red segment, because then this minimum is blocked. It cannot move forward. So now I'm assuming that I have a minimum and it's about to disappear, to change, to evolve. Okay. Then you conclude that on the left you can always have this configuration, which is down and then up. And in this case, yes, indeed your minimum can disappear and you can evolve into this configuration. But if you are in this configuration, what it means that you already have another minimum, which is just 2 sides far from you on your left. So which means, okay, you can evolve, your minimum can evolve only if there is another minimum on its left 2 sides far. Okay, so this implies that the minimum is conserved over the dynamic. Okay, but there is something else that as well you can conclude from this. First, there's something trivial, which is that all the sides of the lattice where the minimum is reached are either all even or all odd. It means they all have the same parity. Okay, this is like a trivial. Why? Because between 2 minimums, you have the same ups and downs of the height function. Your height function will go the same ups and downs, which means that there is an even number of the lattice sides between 2 minimums. Okay, it means that any 2 minimums have the same, either both odd or both even. Okay, but as well, what this figure this illustration shows as well, that this parity is conserved. If you start with the configuration with all the minimums are even, then you will always have a configuration with even minimums, and the same for odd sides or odd minimums. Okay, which means that we have actually 2 ergodic components. Okay, so the ergodic component, which is related to the minimums with even sides, and the other one which is related to the minimums with odd sides. These 2 ergodic components are just related by translation of one side. Okay, so and you can let's say have a representative of these 2 components. You can by the 2 antiferromagnetic states, which is just void particle, or the other way, particle void. So here you'll have even minimums, and here you have odd minimums, and each of these states belong to one of the ergodic component. You can take it as representative. Okay, so there is a ergodic component. It means, of course, the stationary current, average stationary current, is 0. Okay, one important property of this system is that there is an invariant measure, which is provided by this symbol expression. Okay, this invariant measure is their ergodic component, of course. So Q, now B, I took B as 1, so I don't have B anymore in this formula. So it's Q to the power of some energy of the configuration. And the energy of the configuration is given by this function here, which seems like, which seems as if we are integrating the height starting from the minimum height. Okay, if you do that, then you get a quantity which is conserved by translation. Okay, this quantity you can maybe have slightly similar representation if you represent it by a path which is the same as the height path, but you start from one of the minimums. So if you start from a minimum, then your height path will always be above 0, right? Then this actually you call this is a dick path, okay? And these energies will simply become just the area under the dick path, which is here, like for this example, it's just 4. Okay, the gray squares. Okay, you don't count these half or these triangles. Okay. Okay, the invariant measure. Well, why? First, 2 questions: why this is an invariant measure? Second, like what I claim that this is a reversible measure. Okay, if you take 2 configurations of the system, you can prove that they can be related by this equality, which is the property of the reversibility. But as well, this proves that this measure is a stationary one. If you can prove that, okay. But how do you prove this? Okay, first, if you take 2 components which are two configurations which are not related by any swapping, then this is trivially verified. So you have just 0 equals 0. So then what we take eta prime to be a configuration that you obtain from eta by swapping 2 sides. Okay? So eta k plus 1. This is the is the same as eta, but you swap the sides k and k plus 1. Okay. And if you do that, then you can actually relate the energy of the 2 configuration eta and eta prime. Actually, the energy of eta after swapping k plus 1 is the same as the energy of eta plus eta k minus eta k plus 1. Okay, and then now you can just replace this energy by the expression of the invariant measure and verify that actually the equality here holds. Okay, of course, this has to be true only for if eta prime k minus 1, eta k minus 1 is 0. Otherwise, it's again trivially true. Okay. Okay, then you can as well, once you understand that, once you are convinced that this is the ergodic, this is the invariant measure, we can understand what is like the effect of changing Q here. Okay? So let's say if Q is large, then the favorable configurations are is where this dick path has the biggest area, which means it's a state where all the particles are assembled together. So let's call it, this is a ferromagnetic state. And if Q is smaller than 1, imagine, let's say it's very small, then just the most favorable configuration is the configuration with the minimum area for the height path, which is just a configuration, empty full, which is called the anti-ferromagnetic state. Of course, there are 2, as I've just said, and this ferromagnetic state, these 2 particles here, they can be anywhere, but what they have to be is they have to be together. Okay. Okay. Then now the question is how to compute the partition function, because this is what is left for the environment. And this is an important question, especially from physics point of view, because if you want to compute quantities or study the asymptotic behavior, then or study whether there is phase transition, then you need the partition function. Okay. Well, first, this is the definition of the partition function, simply from the expression of the invariant measure. But okay, instead of summing over the configuration, assume that let's imagine that use again the height paths. Okay, so I sum over all the height paths and this and q to the energy of each path. Okay, so this quantity, you can maybe, it looks very similar to another quantity, which is like, okay, if you take, instead of the height paths, the dig paths, okay, and the energy you replace by the area, then this quantity is known in the combinatorics literature. It is called the q-Catalan numbers, okay, by Karlitz and Yodan, because there is multiple q analog of Catalan numbers. This is one of them. Okay, so here I add over all the dn's are the set of dig paths. Okay, but the problem is that these two sets, the height paths and the dig paths, are not isomorphic. Actually, they don't have the same cardinal. So dn, the cardinal of dn is the Catalan number. Okay, so which is given by this expression 1 over n plus 1 choose 2n n. While of course the the cardinal of the height path is just 2n n. Okay, but okay, it's not fair to compare both of the sets. What you have to rather compare is the class of equivalence by translation of dn of hn, okay, with dn. Okay. So the class of equivalence by rotation or by translation. But is it now the same as dn? Okay. So now if you have a site with one if you have a path with one minimum, then actually all the translation of this path can lead to one dig path. Okay, but if you have paths with different minimum, then each time you correspond your path to one dig path from, then through a minimum that you can correspond two different paths to the same dig path, because you can translate them from different minimums. So again, there is no bijection between these two sets, and the problem appears because especially it appears for paths with multiple minimums. So somehow we need to keep track of these multiple minimums. You can, if you want to, like, there is a degeneracy for these paths. Okay, so in order to tackle this problem, I introduced the QS Catalan numbers, which are defined by two variables, not q and s, and s. You sum over all the paths, the q to the power of area of the path multiplied by s to the power of the minimum of the path, m, the number of minimums. Okay, minimum of mw, and mw is the number of minimums of paths, excluding the origin and including the last site. Okay, so this is the number of returns to 0. So for instance, for this path, you have 3 mw equals 3. Okay, of course, if you have s equal 1, then this quantity is just reduced to q-Catalan numbers. Okay. First lemma about these numbers is that they verify the recurrence relation. Okay. Well, this of course has first theoretical importance, this lemma, because then you can study their properties, but as well in numerical importance, because once with this recurrence, now you can numerically evaluate quite efficiently these polynomials. Okay. How do I prove this this relation? First, I have to define what is called elevated dig path, and the elevated dig path is just a dig path that doesn't touches the zero except at the extremes. Okay, so for instance, this is an elevated dig path because it doesn't touch the abscissa. So in other words, MW will have to be 1. Okay. So now if you restrict this partition function to elevated dig paths, so let's call this quantity Gn hat. Okay, so I'm adding over all the n hats. Then this elevated generated function, you can relate it to the same Gn minus to Gn minus 1. Okay. And how do you do that? Well, first you can identify a dig path which is not elevated, but on a lattice which has n minus 1 sides. So this blue path belongs to the lattice, to the side of n minus 1, and it's just a path. It's not necessarily elevated. Okay, and then you can now relate the two quantities. First, of course, MW is 1, so the S goes out, and then you have to just to count the difference of the area. So this the elevated dig path, the black one has more squares, more area, which is exactly n minus 1 than the blue one. So you have this Qn minus 1 factor that goes out, that factors out. Okay, the second ingredient that you need to prove the recurrence is that first you need to notice that if both of the quantities m and number of minimums, number of returns to 0, and the area are additive with respect to concatenation of dig paths. So if you join two dig paths, of course the area is additive, but as well the number of minimum, it's defined so that it is additive actually. So now, okay, so let's say now if you take a random arbitrary path like that, what you can do is that you can cut this path on the first return to 0. So I will cut it. So I will identify two paths. Okay? So the green one and the rest of the path. So the green one is an elevated one because I cut on the first return to 0. The second one is not. It's just a normal path. Now this cut. Okay, let's say it happens at a site k, and it can happen at any site of the lattice. But it allows you to go back again to the definition here and establish a recurrence between elevated dig paths and normal dig paths. So which has this form, which is simply like you assume that this point k can be anywhere on the lattice, and then each time the set of all of the paths, all of the paths can be decomposed into Cartesian product of set of elevated dig paths. Let's say if you fix k, imagine k fixed. You have Cartesian product of set of elevated dig paths on the left and normal dig paths on the right, and then if you translate this Cartesian product into just normal product through the previous relation, then you get this recurrence relation. Okay, now simply the elevated dig path has already it was computed in as a function of Gn, and then you can have this recurrence. Okay, so this, of course, this is not like very, in a sense, this is not very original as a proof. It follows the logic of standard methods in combinatorics, and in particular, I refer to this paper, which treats this sort of world. Of course, it wasn't applied to this particular q-Catalan numbers, but there is like other types of 2 parameters Catalan numbers that were addressed in a similar fashion. Okay. Now, something else that is very useful, which is the generating function of the q-Catalan numbers, which is defined this way. Simply, you add over all the n gn qs xn, and this is interesting because now you can convert the previous recurrence relation into a q functional equation, and you simply multiply both sides by x to the power of n and use sum over n, and you find that this generating function now verifies this equation. Okay, usually this is like useful to extract asymptotic behaviors and many other properties. Okay, we can of course continue talking about q-Catalan numbers, but what is important is for me is to compute my partition function for the model. Okay, so here there is a lemma that I use to compute the partition function, which is okay. My partition function is related to q-Catalan numbers by this simple expression. Okay, you just integrate gn qs over s from 0 to 1 and you multiply by n. Okay, so how can you prove that? Well, first you can prove that what you have to prove is that what you can show that the z and q actually has this expression. So this is like very similar to what I just said a few slides earlier, which is that there is a multiplicity which is related to the number of minimums per dig path. Okay, so you just divide n by this multiplicity, and then that would give the correct factor. And this is of course the same as the integral of from 0 to 1 of gn qs. If you look at the definition of this at the definition of gn. Okay. If you look at the definition of gn, if you integrate integration with respect to s, would become simply this would gives this factor. Okay.
Sorry, so little n was the number of particles in the system. Little n.
Yeah. Sorry. Yes, n is the number of particles in the system. Yes, correct.
And it has to be a prime number for this.
Okay. So yes. So here I wrote it prime number because it's easier to show for a prime number. But actually, this is true for even for non-prime numbers. But for prime numbers, you don't have the problem of multiple. Okay, well, let's make this better. So the class of equivalence by rotation for n prime are all have the same size. So if you don't, if n is not prime, you can have a class of equivalence by rotation or translation, or this, which are not equal to the system of the size the size of the system, but might be like, let's say, half of the system of the size, or a third if n is a multiple of 3, or. But so it's in a sense it's easier. But this happens to be true for any, even for not prime numbers.
Okay, thanks.
Okay, now, one corollary of this equation, which is that the highest n-1 term of ZNQ and NCNQ are identical. Okay, this is not very difficult to prove. Okay, I will not prove it here. Okay, now we can study the asymptotic behavior of ZNQ. Okay, first, ZNQ and NCNQ, for Q bigger than 1, they behave very much the same. They behave very, very close to each other. So for more precisely, the limit of the ratio for n goes to infinity is simply 1. Okay, but C and Q, okay, we know how does this is just a classical quantity, so it has an asymptotic behavior which is given by this expression. Okay, which means now that that Z and Q, okay, behave like Q to the power of n squared. For Q equals 1, you can compute exactly the Z1 and Zn1 and Cn1 are related by symbol factor. Okay, for Q smaller than 1, okay, here the q-Catalan numbers and Zn, they start to differ a little bit, because we just saw some slides ago that when Q is smaller than 1, then the most favorable state is the antiferromagnetic state. So, but actually what you can say is, okay, there are now more minimums, and if there is more minimums, that now we need more the q-Catalan numbers. The degeneracy is higher, and you differ, but you differ. They are still comparable in the sense that their ratio converges to some function. Okay. So, okay, this means that Znq has this form, which is some function of q to the power of n multiplied by a factor. Okay, then I verified this numerically, and by drawing logarithm of Znq. So logarithm of Znq should behave like n squared. This is what indicates that there is some phase transition for q equals 1. So log Znq for q bigger than 1 behaves like n squared. So if you plot the root square of it, then it's just a straight line. And this is true for n, for Zn, or for NCN. Okay, for q smaller than 1, then this quantity behaves like linearly. So in particular here, I plotted Znq to the power of 1 over n as a function of n. So it converges to a constant, which is just this beta q. And beta q can extract it numerically. It's the root of hypergeometrical functions. Okay, I'm not giving here the expressions because it's not relevant. Okay, some other quantities that I am interested in, which is the area of average area of a dig path, okay, or average area or expectation. So this is defined as in this expression, awq to the power of aw, and you can compute it from using the partition function. Okay, for q equals 1, you can have an exact explicit formula. For q different from 1, you can extract the asymptotics from using the previous asymptotics of Z and Q. So we get something which is for q bigger than 1, the average area is like n squared. So it's as if it's as if the height of this big path, the maximum height is of the order of n, okay? And the base is n squared. So it's like almost a full, almost you have, again, now more mathematically, you have a ferromagnetic state, okay? For Q smaller than 1, so this average area grows linearly, which tells you that the typical height of the Dick path is of the order of unity. It's just finite, okay, which means that most of the states are actually, there are many minimums, and the state looks more like an antiferromagnetic state. If Q equals 1, then you have the exponent 3/2, which is just mean that now, okay, now your Dick path is simply Bernoulli random walker. Okay, it's nothing special. The height, the average or the typical height is just root of n. Okay. Yes.
What is beta?
Sorry?
What is beta in the last?
Beta is the same function as here.
Okay.
Which is as well, which is the stationary values for these curves here.
Okay.
I don't. Okay, so I don't write explicitly what is beta because we don't know what is explicitly. It's a root of hypergeometrical functions, and okay, you can just compute it like numerically. Okay, some other quantity which can be interested is the variance of the area. It's defined like that, and you can relate it to the partition function and the other quantity in this manner. Okay, for Q equals 1, you can compute explicitly this expression. I found this. Okay, for Q, for other values of Q, it's the behavior is even more astonishing. So for Q is bigger than 1, the variance is of the order of is bounded. It's not dependent on n. So it's very the fluctuation that you don't, when you are close to the ferromagnetic state, you don't fluctuate much. For Q smaller than 1, when you are close to the antiferromagnetic state, you fluctuate of this order of n. But what you fluctuate a lot when Q equals 1. Okay, it's this order. Okay, then we were interested in the weakly asymmetric regime, which means that, okay, now I'm going to scale the asymmetry parameter Q, and I'm writing it in this form B over n to the power of alpha, where n is okay, it's not the system size, it's the number of particles, which is half of the system size. Okay, then now you can re-ask all of these previous questions, but not as function of Q, but now as a function of two parameters, which are B and alpha. For instance, okay, I choose one example, which is the variance, and here now I have much less analytical tools, so I mostly relied on numerics. So this part is still under investigation, and okay, we found that there is indeed rich behavior of terms of the asymptotics as a function of B and alpha. Okay. In particular, the value alpha equals 1 seems to be an important value where the scaling changes. Okay. So here the scaling changes from 1 plus alpha to of the asymptotics. So there's some perspective of this work. First, I would like to understand the invariant measure and the hydrodynamics for systems which are smaller than the half-filled systems. Okay, I would like to investigate whether there is some phase transitions in the weakly asymmetric regime, because here on this blue segment, it's still not clear what is the behavior. Probably there will be something which scales differently according as a function of b, but this is still under investigation. Okay, I would like to understand better the relation to the ABC model. And the ABC model, if you know, it's a model with two species where the dynamics is cyclic. So which means that species A jumps over B, jumps over C with some rate, and C jumps over B, jumps over A with different rate, and with a different rate, which is 0. Sorry, with a difference, not with it, yes, they can jump only in one direction. And in this in this model, you can as well usually it's studied in a system which is third field. So they put third of the system of particle A, third of the system of particle B, third of particle C, and you observe similar phenomenology in terms of, for instance, clustering of particles. So there's some asymmetry parameter, and the clustering of the particle appears for large value of the asymmetry parameter. So there is lots of analogy to our model, but the exact relation is still to be investigated. Last thing is, I want to compute the correlation functions for this model and see if they give some more insights or more information about the transitions between the phases. Okay, thank you.
Thank you very much. Let's see if there are questions or comments from the audience. So everything you said, I mean, I guess it relies a lot on the fact that you have a boundary condition, periodic boundary condition, no?
Sorry?
So you rely a lot on the fact that you are under periodic boundary conditions.
Yeah, absolutely. So if there is, the question of half filling is not, so actually it's a sensitive property. So even if you add one more particle or remove one more particle, then everything is destroyed. It's a bit very strict. So the half filling is strict, and the half filling is meaningful only for periodic condition. So
I see. Well, so this model is in the class of kinetic constraint model, I guess.
This I'm not sure I know. You can maybe tell me more. Why do you think so, or what is?
Okay, no, just no, because the dynamics sometimes is prohibited if there is or there isn't a particle in the appropriate.
Okay.
So let's see if there are more comments or questions. It's not. Okay, so if there are no questions, so thank you very much, Ali, for the talk. And we update next Wednesday at the same time here. Okay. Bye-bye, everyone.
Bye-bye.